So today is the second class of D and A block elements. So in this, I will discuss about the ionization enthalpy and then oxidation state and electrode potential. So first of all, we have to know that what is the ionization potential. What is the ionization enthalpy or the ionization potential? You can say that because ionization enthalpy is that this is the sum amount of the energy is that needed to remove the last electron from the valence shell of the element. It is called the ionization enthalpy. So in this case of the 3D metal case, this is the transition metal case, the position metal case. There are we know that these are the elements, these are 3D metals element scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and the copper. And there is the zinc is present. So, so today we will know about the ionization enthalpy value of this three of these 3D elements. So, what is happening here? We will know first of all this is the first ionization enthalpy. This is the second ionization enthalpy. This is the third ionization enthalpy. The first ionization enthalpy means that there is the loss of one electron. Second ionization enthalpy that means that so suppose the first ionization so m to the m plus m to the m plus so this is the first ionization enthalpy. Second ionization enthalpy means the m plus 2 the m plus 2. Third ionization enthalpy means m plus 2 to m plus 3. So these all are the ionization enthalpy value, but this is the first, this is the second, and this is the third. Now there is a comment is that there is an increase in the ionization enthalpy along the each series of the transition element from the left to the right. Once we are going to this scandium to titanium to vanadium or this chromium, that means that when we are going to this left to the right center, then this value is the increasing. For the scandium, the first ionization value is 631 kilojoule per mole. But for the titanium, it is the 656. It is a 650 for this vanadium. Chromium is the 653. So this value is the gradually the increasing. But point is that this increasing value is the very uh, low compared to if you compare to the second and this third ionization enthalpy value. So that's why it is the written that this value is increasing left to the right. But why this value is the increasing? When the, for the scandium it is the 631, for this titanium it is the 656. It is the increasing due to an increasing in the nuclear charge, which the accompanies the filling of the inner T orbital. That means that when this scandium, its electron is 21 atomic number, it is 22, it is 23, it is 24, this is 25, this is 26, this is 27, this is 28, this is 29, this is 30. So once we are moving from the left to the right, then the one electron is added to this d orbital. Once the one electron is added to the d orbital, simultaneously this nuclear charge, this jet effective nuclear charge is increasing. When this nuclear charge is increasing, then consequently this effective nuclear charge of this on this last electron, on the last electrons, the effective nuclear charge also the increasing. So when this effective nuclear charge also the increasing, so Z this value is increasing, so Z effective value is increasing. So when this value is increasing, then this last electron is most folded by this nucleus. So to release this electron, this last electron, to release this last electron, it needs this amount of the extra energy than the previous atom. So that's why the some amount of the ionization enthalpy value is increasing, but it is not too much increasing because there is reason is that suppose this is the nucleus, this is the d orbitals. So when this one electron is here, So when this one electron is entering this the orbital, so this effective nuclear charge of this electron is increasing. So the effective nuclear charge or this nuclear charge, this value of this nucleus is increasing. But simultaneously, d orbital, when this d orbital in this d orbital electrons is increasing, there is the some effect of this electron to repulsion. Okay, there is the electron to repulsion is there. Electron to electron repulsion is there. So due to this reason, actually, this effective nuclear charge is not more effective on the last electrons. That's why the some amount of the extra energy is needed to ionize uh, for these 3D metals. So that's why this value is increasing, but not in large extent. And there is the three terms also we can explain of this fact. First of all, the attractions of the s electrons towards this nucleus. Already that is the Z effective nuclear charge. Already I have discussed here. Another is the repulsion between these electrons. Already I have told here. When these electrons is entering these d orbitals, so they are also the repulsion. That is the repulsion between uh, between the electrons. So due to this presence of this repulsion, so when this electron repulsion is there, so once electrons will have the greater chance, once electrons will have the greater chance, greater chance to escape from this place, from the d orbitals. So when this repulsion is greater, so then there is a more chance, the entropy is increasing. So there is a more chance to escape from this d orbitals. So that's why this due to the repulsion, this value also is not too much extended. Another thing is the effective nuclear charge. Second thing, we will know that exchange energy. What is that? This is a very interesting exchange energy. For that exchange energy, what is happening? So we know that this is the 3D orbital. Suppose this is the 3D orbital. So this is the 5D orbital is there. One, two, three, four, five. So suppose there is the three electrons is present. So this is the D3 electronic configuration. And these 5D orbitals are degenerated. So degenerate, this means that the energy of the degenerate, this means that energy of 5D orbitals are same. So these 5D orbitals are in the same energy. That's why these 5D orbitals, this is the suppose that dxy, dyz, dxz, and dx2, and dx2 and y2. So these 5D orbitals have the same energy. That's why these orbitals are called degenerated orbitals. When these 5D orbitals are in degenerate, then we can exchange these electrons, this orbital to this orbital. So here we can write another electronic environment like that. And also these electrons can move there. Okay. And also these electrons can be here. Because these 5D orbitals, whatever the orbitals is there, all orbitals are in the same energy state. So electrons easily can move one orbital to this another orbitals. So this is called uh, 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 that actually we can say that this exchange energy is approximately proportional to the total number of possible pair of the parallel spin in the degenerate orbitals. Already I have told that. So when we have seen, so this is the one type of, suppose again I have written here, suppose this is the one environment, for these two electrons. So this is suppose the D2 electrons configuration. So another we can write here also. Uh, Another also we can write here also. So so in this way we can arrange the electronic environment. We can arrange the electronic environment. But but the so in this array, this electrons can exchange this one orbital to this another orbitals. But everywhere you can see these two electrons are in the parallel space. When this exchange energy, the loss of the exchange energy, when this the loss of the exchange energy uh, uh, is actually increasing the stability. Okay, so when there is the number of the possibility of the exchange energy is the more greater, then it will have the more stability. When it will have the more stability, then the ionization is the more difficult, because in this electronic configuration, in this electronic environment, it is more stable. It is more stable. So it will this electronic environment not ever wants to get unstable electronic environment. That's why it is written here: the loss of the excess energy increases the stability. As the stability increases, then the ionization becomes the more difficult. So according to this Holmes rules, actually it is written here, because we know that according to the Holmes rules, this one these electrons can these orbitals will be filled up by this one electrons one by ones. When this lowest energy orbitals will be filled up, then it will go to higher energy. When this orbital still filled up by the six electrons, then these seven electrons will go to this higher energy. Uh, so this actually the constraints. So with these five rules, here we have applying this exchange energy to get the ionization enthalpy value. So here the electrons are added to the orbitals of the inner subsets, that is the 3D orbitals. When these 3D orbitals that steal these forest electrons from the increasing the nuclear charge is somewhat the more effectively. So this is actually for this nuclear charge. So this is for the second point. Okay. So this whatever already I have told in the second point. So this is actually the third point for this exchange energy. So with this exchange energy concept, here I have written some question. There is the two question is there. First question is that ionization enthalpy of Mn plus is lower than the chromium plus. So first of all, we have to know what the electronic configurations of the Mn. We know that Mn, that means is manganese. So it is the electronic configurations is 3D 5 4s, because the atomic number is 25. So the electronic configuration is 3D 5 4s2. When it is the Mn plus, when it is the Mn plus, so the electronic configurations will be the 3D 4 4s1. Similarly, you can also see this the chromium. Chromium, the electronic configuration is 24. So the electronic configuration is, sorry, this is the atomic number is 24. So the electronic configuration is 3D5 4s1. It is the exceptional. When it is the chromium plus, then the electronic configuration is the 3D5. Now, in this state, we want to ionize this manganese plus 1 to this manganese plus 2. One electron is removed. And in this state, it is the chromium. It will be the remove this chromium plus 2 and remove the one electrons and oxidize to the chromium plus 2. So, whatever ionization enthalpy we are telling here, this is the second ionization enthalpy for this manganese, and this is the second ionization enthalpy for this chromium. So the question is that ionization enthalpy of the Mn plus is lower than this chromium plus. So here this Mn, so the delta H2 Mn, this value is lower than delta H2 this chromium. Now the question is the why? Because if you say, you can see that for this Mn plus 1, the electronic configuration is the 3D5 4s1. Yet, if it is the remove this one electrons anywhere, anyhow, uh, it it can remove this one electron from this 4s. The electronic configuration for this manganese plus 2 will be the 3d5. And 3d5, so you know, this is the half-filled electronic configuration, so it is the more stable. Second thing is that it is the 3d5 electronic configuration. That means there the loss of the excess energy is more, so it increasing the more stability also is there. Okay, because here we can see that there is a five unpaired electrons, and these five unpaired electrons are in the same parallel spin, and these five unpaired electrons are present in the 5d orbitals, which are actually degenerated. So easily these electrons can exchange their the position from to each other. So the exchange energy is the very less for the loss of this for that case. Okay, so the exchange energy is uh, that's the very less. So the stability is the very high for this 3d5 electronic configuration, and it is also the outfield. That's why if this manganese Mn plus 1 always wants to go, this Mn plus 2 always wants to go the 3d5 electronic configuration, it is the outfield. That's why this electronic configuration, this delta H2 for this manganese will be the lower or than the chromium, because in case of the chromium plus 1, the electronic configuration is the 35. If it is the chromium plus 2, so one electrons will be the loss, then the electronic configuration will be the 34. But if you compare the 35 and the 34, 35 is the half field, it is a more stable. So when it is a more stable electronic configuration, then to ionize this one, to ionize this chromium plus 1 to the chromium plus 2, to remove this one electron from the 5 electronic configuration, it will have the greater energy to get this 34 electronic configuration. That's why the ionization enthalpy value is the higher than compared to this manganese. So this is the first question answer. Second question answer you can think about in this way. This ionization enthalpy of this iron plus 2 is the lower than this Mn plus 2. Here also you can see the iron, it has the atomic number is 26. So electronic configuration is 3d6 4s2. So when it is the iron plus 2, then the electronic configuration will be the 3d6. But in case of the manganese, already I have written for this manganese plus 2, it has the electronic configuration is the 3d5. Now the ionization. So here we suppose the one electron reductions. So sorry, one electron oxidations. So the Mns will be the Mn plus 3, and the electronic configurations will be the 3d4. But here also, if you remove this one electrons from that Fe plus 2 electron, then the oxidation state of the iron will be the Fe plus 3, then the electronic configurations will be the 3d5. Now, in case of the 3d5, it is the half field, it is the most stable, and it is the 3d4. So the iron plus 2 will easily oxidize to the iron plus 3, because it will get the half field electronic configurations. That's why the ionization enthalpy value of this iron plus 2 is lower than the Mn plus 2, because everyone wants actually to be the stabilized. So that's why the iron plus 2 easily wants to removes this one electrons and to get this half field electronic configuration. So with this half field and full field, and with this exchange energy concept, you can answer of these two questions. So this actually are the related. These are the important questions that related to the ionization enthalpy of the 3D metal elements. Second, there is the another question. The why the second ionization enthalpy value of this chromium and this copper is the high. For that chromium and this copper, the second ionization value why the high. So already I have told for this chromium case, because when we are talking about this second ionization enthalpy value, then you have to write first of all this electronic configuration of the chromium plus 1. The chromium plus 1 electronic configuration is 3d5. So when we are talking about the second ionization enthalpy, then we have to remove the one electron from the 3d orbitals. So it will be the chromium plus 2. So then it will have the electronic configuration is 3d4. So it is the half field, it is the stable. So that's why it is the high for that chromium case. Now for the copper case. First we know that the atomic number is the 29. So the for that copper, the electronic configuration is 3d10 4s1. So when it is the copper plus 1, then it will have the electron configuration 3d10 4s0. Okay, because one electron is the removed here. But here we are talking about the second ionization enthalpy. So we have to remove this one electron on these 3D orbitals. But you see the 3D10, D10, this is the full field already. Okay, this is a full field. It's the more stable. Uh, more stable. That's why when we remove here this, it will be the cobalt plus 2, then the electron configuration will be the 3D9. But to remove this one electron from that full field d orbital, it is not a easy task. That's why the second ionization enthalpy value for that copper is the high value. It is the giving this high value. You can see that chart here for that copper case. This is the first ionization enthalpy. This is the second ionization enthalpy. This is 1958. It is higher than other actually 3D metal. For that chromium also, it is the 159. So first is the copper because it is a full field. One electron is removed from the full field. One electron removed from the full field. Another for the chromium case, one electron is removed from the half field. And we know that the full field is the more stable than the half field. That's why for that copper case, the second ionization enthalpy value is the higher than the chromium case. Okay, it is the 1958 kilojoule per mole. It is the 1592 kilojoule per mole. There is also the comparison. So these are ionization value, and why this ionization enthalpy is greater than less than that actually discussed by this three factor. One is the attractions of the electrons toward the nucleus, it's the effective nuclear charge. Another is the repulsion of the electron. Third one is the exchange energy, and also you can explain by this half field full field stability. That is actually the exchange energy theory. So these are actually ionization enthalpy related questions, and this is the concept of the 3D metal case. Now we will talk about the oxidation state. Now the oxidation state. So when we are actually ionize this scandium, titanium, vanadium, suppose the scandium one electrons ionized. So it will be the scandium plus one. So this is the plus one. This is actually the oxidation state. Whatever charge will be present on the top of the metal, that will be the oxidation state. Now for that today metal, the common oxidation state or the lowest oxidation and the common oxidation state is the plus two. Here you can see that except the scandium, the titanium has the oxidation state plus two, radium plus two, chromium, manganese, iron, cobalt, nickel, copper also the plus two, and zinc also the plus two. So the common oxidation state of the 3D metal is the plus two oxidation state. But there are the some question is that first of all I will talk about the scandium. Why it has the plus two oxidation state? Because you can see that for the scandium the atomic number is the 21. So the electronic configuration is 3D14s2. When it will be this scandium plus 2, when it will be the scandium plus 2, the electronic configuration will be 3D1. But when it will be the scandium plus 3, then electronic configuration will be the 3D0. So this is actually following when it is the scandium plus 3, then so there is no electron in the d orbital and the post orbital. So the electronic configuration for that scandium, sorry. just a minute. So for that scandium case, when it will be the scandium plus 3, then the electronic configurations will be, the valence electronic configurations will be 2s, 2p, uh, 3s, and 3p. So this is a 3s2 and 3p 6, 2s2 to p6, 2s2 to p6, and 3s2 3p6. Then the 3D is 0, and this is then the 4S 0. So it is actually following the inert gas electronic configuration. Uh, so it is the more stable. That's why it actually this scandium is going to the plus 3 electronic configuration rather than the plus 2. Other metals will have the reasons. There is the general electronic configuration is the plus 2. So here another point is written: the lesser number of the oxidation state at the extreme end stems from the either the too few electrons to the loss and the share. So here you can see that the electronic oxidation state diagram is like that. That means that the left side elements will have the lower number of oxidation state, and right side elements also will have the lower number of oxidation state. But the middle portions will have the larger number of the oxidation state. Okay, for that titanium, it will have the plus 2, plus 3, plus 4 oxidation. When we are going to this vanadium, it will have the oxidation state plus 2, plus 3, plus 4, plus 5. Because vanadium is the 23, it is the 24, the one electron is increasing, oxidation state is the plus 6. It is the 25, oxidation is the, it is going to this 7 electron oxidation. When it is the iron, then it is a 26. It is going to the 6 electron oxidation. When it is the 27, it will be the 4 electron configuration. It is the 28, then it will have the highest the 4 electron configuration. For that copper, it will have the 2 electron configuration. For that zinc, it will have the 2 electron configuration. Uh, so this is the one strength you on the series. You can see that the left side and the right side elements will have the lowest number of the oxidation state, but the middle portions, what about the 3D elements in presence in the middle, uh, that have actually the higher number of oxidation state. For the titanium, here the manganese, uh, suppose the manganese have the 7 oxidation state, is a Mn plus 7 Mn. Actually, this is the Mn4 minus. It will have the plus 7 oxidation state. For that chromium, it has a plus 6 oxidation state. This is the vanadium, which is a plus 5 oxidation state. So these are actually the highest oxidation states the oxide are the present of the 3D metals. Okay. So this is actually the general view of the oxidation state of the 3D metal. Now, there is the some question. One question I have written here. In the group 6, you can see that molybdenum and the tungsten are the found in the plus 6, and the plus 6 oxidation state is the more stable than the chromium plus 6 oxidation state. It's a very interesting thing. Here, what is actually written in this fact, it is like that is that when we are going to this chromium, then the molybdenum, then the tungsten. So this is the 3D orbital, 3D series element, 4D, and this is the 5D. Okay. It is an answer of question is that once we are going to this 3D to 4D, and when we are going to this 4D to the 5D orbital, then the electrons actually is removing from or that chromiums when it is a chromium 6, the molybdenum 6, and this is the tungsten 6. All that case actually, the electrons are the removed from this d orbitals also. This is the 3D orbitals and the 4s orbital. Here the electrons are the removed the 4D orbitals, and this is the 5s orbitals. And for the tungsten, the electrons is removed from the 5D orbitals, and this is the 6s orbital. Now there is a question is that why in this group 6 for that molybdenum and the tungstens are the found to a more stable plastic oxidation state compared to the chromium. Because the stability of the oxidation state increases the downstream group due to the easier availability of the both the D and the S orbital or the ionization. When we are going to this plastic oxidation state, that is actually the ionization. So when we are going to the plastic oxidation state, that means the ionization. First ionization, second, third, fourth, fifth, and the sixth ionization. After the sixth ionization, we are getting the chromium plastic oxidation state, then the molybdenum plastic oxidation state, and the tungsten plastic oxidation state. But the question is that when we are going to the 4D and the 5D orbitals, then there is the availability of the electrons. This electron, what are the d orbitals is there? Whatever the electrons are the present in the d orbital and the s orbital for that molybdenum and the tungsten. These are actually very easy to remove from the 4D and the 5D orbital because when we are going to this, suppose the tungsten, they are the present is the 4F orbitals. So another effect is that the inert pair effect is present here. So there is the 4D syndrome is there, or we can also say that when we are going to this 4D and the 5D, then this or these electrons, whatever presents to the 4D orbitals, 5D orbitals, these electrons actually move more away from this nucleus compared to the 3D orbitals. So there is the easy availability of the both the d orbital and the s electron for the ionization. So this is the more easier availability of the d and the s orbital occurs as the higher energy in d and s orbital like the 2D, 5D, 3s and the 4s orbital. Because if you compare, this is the 3D, this is the 4D, and this is the 5D. So this is the energy profile diagram. You can say this is the 4D and the 5D are the higher energy state compared to the 3D orbital. So whatever electrons is present here, these electrons can easily remove from the 4D and the 5D orbitals because here the effective nuclear charge on the 4D orbital and the 5D orbital is the very less compared to the 3D orbital. Because the 3D orbitals, the when the principal quantum number is the 3, then it is the more closer to the nucleus. So it will have the more effective the nuclear charge compared to the 4D and the 5D orbitals. So remove this one electrons or the six electrons from the 45 orbitals is the very easier than the 3D orbitals. That's why this the molybdenum and the tungstens are the found to be the most stable in the chromium plastics. It is also compared by this p block element. We know that p block elements are very stable in the lower oxidation state because there are the inert pair effect is there. When is the inert pair effect? That is the unavailability of the forest electron because there is the inert pair effect. So due to the presence of this inert pair effect, uh, whatever electrons are present in the s orbital, these actually are more attracted by this nucleus because the inert pair effect is there. So there is the pore shielding, pore shielding effect of this f orbital and the d orbitals for that p block element. So because so that's why the s electrons is not easily available to remove from that the p s orbital due to the inert pair effect. So this is the another case for the p block element, but it is the similar. It is totally opposite to the three transition metal. So when we are going to this three to four D IFD orbitals, then we are we are going to the more I from the nucleus. So the effective nuclear charge will be the less effective over the 4D and this 5D orbital compared to the 3D orbitals. So whatever electrons are the present in the 4D and the 5D orbital, these are the more easier to use. These are the more easier to ionize this electron compared to the 3D orbital. That's why the molybdenum and the tungsten, and they are the more found, more stable in plastic citizen state compared to the protein. So these are actually fact. This is actually very interesting question. Uh, Another thing we can also uh, question is that is the titanium plus 4. is the more stable than the titanium plus 3 and the titanium plus. Now the scandium, we know the scandium and then the titanium. So this is the 21, this is the 22. So for the titanium, the electronic configuration is the 3 2 and this is the 4s2. Okay. So when the electronic configuration is the 3 2, this is the 4s2. Now when we are talking about this titanium plus 2 oxidation state, the electronic configuration is 3. When we are talking about the titanium plus 3 oxidation state, the electronic configuration is 31. When we are talking about this titanium plus 4 oxidation state, it is electronic configuration is 30. That means it has the 3s2 and the CP6. So it is actually following the inert gas. So it is a noble gas electronic configuration, noble metal electronic configuration. So it is the most stable electronic configuration. That's why actually titanium plus 4 is the most stable than the titanium plus 3 and the titanium plus 2. There is another comment is that when we're talking about the low oxidation state are the found when a complex low oxidation state, that means we know that the 3D orbitals, whatever the 3D transition elements are present from the scandium to the zinc, to the common oxidation state is the plus 2. When we are going to the low valent or the low oxidation state, that means this is the plus 1, 0, minus 1. So this actually the low valent or the low oxidation state. So when we are talking about the low oxidation state, then we have to think about this type of the metal complex. This is the nickel pure bond 4. This is the carbonyl. This is a neutral. So here the nickel has the zero oxidation state. There is another example. If you use bond 5, here also the iron has the zero oxidation state. Okay, so these are actually the stabilized by this CO ligand. These are actually stabilized by this CO ligand. These are not the freely stabilized. We can not say it is the most stable. The nickel zero is the stable. Not because that is the nickel zero. When we are talking about this nickel zero, the electronic configuration is nickel is 28 to the 3D8 4s2. So it will always to oxidize. In presence of the oxygen. So it will always, and two electrons will be removed and it will form this nickel plus oxidation state. So that's why it will have the stabilized, it will be the stabilized by this another electronic effect. This is the CO ligand. Because we know that the CO has the sigma 1 also and the pi acceptor character. Because the CO has the sigma donor also a pi acceptor. Okay, so that's why it is actually stabilized by this pure ligand. And it's your bond 4 and if it's your bond 5. There is the sigma bonding and another is the pi acceptor character is present of this pure ligand. So when we are talking about the low valent, that means it is the oxidation state is lower than the plus 2. When we are talking about the high valent, it is the higher oxidation state from the plus 2. Suppose, so this is the plus 2 is the normal. When we are going to this plus 3 plus 4, this is the high valent. This is the high valent. When we are going to this lower than the plus 2 oxidation state, it is the low valent. Okay, so these are the general, uh, the high valent and this is the normal. This is the normal, or we can say this is the stable. Okay, uh, so from that, the stable oxidation state, from that, the normal oxidation state, we are going to this high oxidation state. Then we will say this is the high valent. And when we are going to the low oxidation state, this is the low valent. Now I will talk about the standard electron potential because all are the related to each other. When we are talking about the standard electrode potential that means there also the electrons is removing. That means the ionization. So first, ionization enthalpy. From that ionization enthalpy, we are talking about the oxidation state because when the ionization enthalpy will be happen, ionizations will be happen, then it will have the some several number of the oxidation state. Similarly, so one electron is removed, second electron is removed. So how much energy is required? That is actually defined by actually the electrode potential. So here, the standard electron potential diagram just is given here. It is like that. Uh, this is the from the titanium. So from the titanium to when we are going to the titanium to vanadium, then the chromium, this manganese, iron. So this the red one is actually the calculated value, and this blue one is the observed value. Okay, so calculated and observed value are the more or less the similar here. Here we can see that. So this is the zero. Okay, so this is the zero. So above zero it is the positive electron potential. Below the zero it is showing the negative electron potential. So here we can see for that copper, only the copper has the positive electrode potential, and the other 3D metals, except the copper, other 3D metals have the negative electrode potential. Now you can see from when we are going to this titanium to vanadium, vanadium to the chromium, then the electrode potential value is the increased. Then from that manganese, then the again the decrease. So here, what electrode potential we are talking about? We are talking about this M2 M plus 2. That means two electron potential, two electron potential. That means second ionization enthalpy. We are talking about second ionization enthalpy. Okay, so here the two electron reduction is sorry, oxidation. Two electron oxidation. Two electron oxidation, because we are talking about this M2 M plus 2. We are talking about M2 M plus 2. So this is the two electron oxidation is happened. So whatever reduction potential is given here, it is actually written in this way, M plus 2 M. So the reduction potential, that means the M plus to the M. Okay. So when we are going to this titanium to the chromium, then the reduction potential value is increasing. Then for that manganese Mn value, Mn, this reduction potential value is decreasing. Then the iron is increasing. Then the again observed value is increasing, and for that copper it is giving the positive, and for that zinc it is also the negative. So there is the three type of the question. You can see for that Mn why it is the decreasing, and for that zinc why it is the decreasing, and why this copper actually giving the positive reduction potential value. This is very interesting question. So first of all, we have to know how this standard electrode potential is defined. Okay, now how we will know the standard electrode potential, how it is actually defined, when it will be positive and when it will be negative. So first we will talk about this copper. Okay, why this copper actually showing this positive reduction potential value. So so copper is, suppose this the copper is solid. So for that metal, and any the three transition metal, this is solid. That in presence of the some amount of the energy, it is solid to the gaseous state. So it is the atomization state. So that's why it's the delta AH. This is the atomization. And this atomization process is the endothermic. Okay. So first the atomization is happened. Then there is the ionization enthalpy is there. Some amount of the energy is needed to remove this electron from that gaseous state. So this is also the endothermic. This is also the endothermic. So it will have the positive value. It will have also the positive value. Now, when it will be the gaseous state in plus 2, then we will react with this aqueous in presence of the water. uh, it will form the Mn plus 2 aqueous. So this is the hydration enthalpy. But here, what is happening when in the gaseous state is react with this aqueous, then some amount of the energy is that released. So it is actually the exothermic. So it will have the negative value. Now with this concept, here we can see that for that copper, first the atomization value is 339 kilojoule per mole. Second, the ionization enthalpy value, it is also the positive endothermic process. This is the 1958 kilojoule per mole. But the hydration enthalpy value, this is the delta H. This hydration enthalpy value is the negative because it is the exothermic. But for that, the electron potential value, it will be positive or the negative. That is actually calculated by the need value. The need value is 339 plus 1958 minus 2121. This value will be the positive 176 around. So it is actually giving this positive value. That's why the electron potential value is plus 0.34 volt. Okay, so it is written here. The copper has the higher value of the atomization enthalpy. So this atomization enthalpy value is the higher, and the low hydration enthalpy, this is the low hydration enthalpy value. As a result, overall the effective electric potential value is the positive because the overall value is the positive. That's why the electric potential value is the positive plus 0.34 volt. So here is the chart. From that chart, you can easily calculate it that easily you can also say that why this copper actually has the positive electron potential value and the other the negative electron potential value. When it will the net value will be the positive, then it will be the positive reduction potential. When it will be the negative, it will have the negative reduction potential. Okay. Now you can see that why this chromium plus 2 is reducing and why this Mn plus 3 is oxidizing when both have the D4 electron configuration. That is actually the fact. So when we are talking about this Mn, this is the standard electron potential value of this Mn. That means it is the Mn plus to this Mn. So this value actually, it is actually lower than this chromium. So this is the chromium plus one, this is the chromium. Now this question is came here. So from that chart, you can see that chromium for that chromium has the chromium plus 2 and this is the manganese plus 2. Okay, it will have whatever the E0 value chromium plus 2, it is greater than this is the E0, this is the Mn plus 2. So when this reduction potential value is higher in same oxidation state, then it will act actually the reducing agent. It will act actually the reducing agent. And here the manganese act actually the oxidative agent. But so that's why it is written here that why this chromium plus 2 is reducing. Uh, because it is a reducing agent. But Mn plus 3 is oxidizing. Uh, why? Because both have the D4 electronic configuration. Because if you see that where it is the chromium plus 2, it has the D4 electronic configuration. When it is the reducing, that means that it will be it actually the reducing. So that means this chromium plus 2, it will take this one electron. When it is the reducing electronic configuration, reducing, that means it is the reducing the another, and it is the oxidized itself. Because the chromium 0 plus 2 has the greater electron potential value, reduction potential value than the Mn plus 2. So it is actually acting as the reducing agent. So when it is reducing to another, then it will be oxidized. So when it is the oxidized, the one electron will be removed, then it will be from the chromium plus 3. Then the chromium plus 3, it has the electronic configuration. You can see that it has the 3 electrons. Okay. Now, talking about this Mn plus 3, it is actually oxidizing another. So it will be the when it will be oxidizing another body, then it will be reduced to its stack. So it will actually taking this one electron, then it is the forming this Mn plus 2. So when it is the manganese plus 3, then the electronic configuration is D4. But when it is the taking this one electron, the electronic configuration is the D5. But we know that D5 is the half filled, is the stable, it is the stable. Okay. So that's why Mn plus 3 easily oxidizing another body, and it will be the reducing to itself, because when when the Mn plus 3 is oxidizing another body, then it is actually forming this Mn plus 2, because it is the taking this one electron from the another body. So that's why it is the forming this Mn plus 2. Then the electronic configuration is D5. Then it is the half filled. It is the stable. But for that chromium plus 2 case, it has the electronic configuration D4, but it is actually act as a reducing agent, because when it will be reducing the other body, then it will remove this one electron from the d orbital. It will form this chromium plus 3, and it is actually chromium plus 3 when then the electronic configuration will be the D3. That means this is the D2Z3. D2Z3, it is like that. So it is actually half filled. Okay. It is also the stable electronic configuration uh, octahedral crystal field theory from that. Okay. So that's why the chromium plus 2 act as a reducing agent here, and Mn plus 3 act as a oxidizing agent here. Another question, that question actually what I have arised here, why this Mn, this value is decreasing? The reduction potential, the standard reduction potential value, uh, it is going to this negative. That means it is going to this Mn Mn plus 2. Uh, there is the 2 electron. Actually, the reduction is happened. This the reduction potential value is given. That means these 2 electrons we have to the put up, or the two electrons actually the removing. 2 electrons is the remove. So, when we are talking about manganese, this is the 3d5 forest 2. This is the 3d5 forest 2. When it is the Mn plus 2, then the electronic configuration is the D5. And we know that this D5 is the half filled and the stable. So, that's why easily it will give the 2 electrons on this D5 electronic configuration. When it will be easily to give this 2 electrons, that's why this reduction potential value is the more negative compared to the chromium case. Okay, because the titanium, vanadium, chromium, when we are talking about this chromium, so the chromium is electronic configuration is 3d5 4s1, but when it is the chromium plus 2, then the electronic configuration is 3d4. But after the one electron reduction, the second electron reduction is the more difficult for that chromium. That's why this value is around 1.2 electron volt, because it has the greater energy. It has the more potential, more current to remove this one electron from this 5 electron configuration. That's why it has actually reduction potential value is higher. That means the lower negative. That means the higher value compared to this manganese. So these are the standard reduction potential. So here one strength I will talk about. It is the strength is the Mn plus 3 and Mn plus 2 standard reduction reduction potential, which is the Mn plus 3 and Mn plus 2. For that scandium, it has the reduction potential value. This is the titanium, vanadium, when we are going over titanium, vanadium, chromium. So these are actually value of the reduction potential value. This is the M plus 3 and this is the M plus 2. So there is the some question is that the low value for the scandium reflects the stability of the scandium plus 3, which has the noble gas electronic configuration. Because we know that this reduction potential value when we are talking about M plus 3 to M plus 2. That means that M plus 3, it will take this one electrons, it will form this M plus 2. So this is the reduction potential value. So for that scandium, we know that plus 3 oxidation state, it is the stable. So that's why it will have actually less the value. Not that zinc, it is giving this highest value due to it is giving the highest value because when it is the zinc plus 2 oxidation state, uh, suppose there is the zinc plus 3. Somehow it is taking the one electrons, it will form this zinc plus 2. When it is a zinc plus 2, then the electron configuration will be the 3D10. It is the most stable. That's why it is giving the highest value for the zinc. It is due to the removal of the one electron from that the stable that detailed electronic configuration. Comparatively, the high value of the Mn, the so the Mn plus 2 is the D5 electron configuration because if you say two electrons will be the removed, so it will form this Mn plus 2, then it will actually giving the D5 electron configuration. That's why it is giving this high value also. Similarly, for that iron case, when we are talking about this iron plus 2, then the electronic configuration is 3d6. 3d6. But but we know that for the 3d6 is not the stable. If we iron plus 3, for that iron plus 3, the D5 electronic configuration is the very stable. That's why it is the very the low value. For the vanadium also case, when we are talking about this vanadium plus 2, it is the half filled because the vanadium plus 2 is the D3 electron configuration. That's why it is going to this low value. Okay, so these are actually some all actually related to the half filled and the low filled electronic configuration. So here I will stop the class, today's class. We will in the next class we will talk about the magnetic properties and color of the 3D metal. Yes. So if you have the any question